Oh, that's a nebulous question to ask.
Let's see. So,
Engineering Design Lab is
Engineering Design Lab is
Engineering Design Lab is a multidisciplinary engineering consultancy that works on a wide range of different complex technical projects.
Essentially, I would say we're professional problem solvers.
it's almost like just calling up your friend. If you're in need, if you're in the middle of a project, and you're like, I don't know, I can't get this thing to work.
One of the lessons you learn as a multidisciplinary design engineer working on these complex projects is that very rarely, even with the most skilled engineers and the best planning and every resource you could throw at a project, very rarely does everything work exactly as planned when you put it all together.
we have people here with a very broad skill set from like circuit development, software development, mechanical development testing, manufacturing support. We do pretty much everything.
We do a lot of work with kind of sustainable mobility, last mile delivery, so focusing on those kind of small electric vehicles that can get around urban areas quickly.
Anything from trucks to mopeds to scooters to all sorts of delivery vehicles. So 1 wheel, 2 wheel, 3 wheel, 4 wheel, and even 7 wheels.
We work with clients who are sometimes startups and they're going and pushing forwards on their first or second vehicle, or they're long-established companies which need to have an expandable branch of their engineering team.
People come to us looking to kind of get different engineering expertise in areas that they may not have in-house, or to quickly ramp up the size of their team.
Anything from large government institutions such as Ontario Power Generation or the Department of National Defence to smaller companies trying to build, say, a new type of electric vehicle and who have never done that before. And so we're basically a set of experienced hands that can come in, help them do that project, help them get to market faster and build the best possible EV.
One of the really interesting things about Engineering Design Lab is that we can approach a project and meaningfully help at any stage from the initial idea to the end of development, or even partway through commercial deployment.
We, again, have a multidisciplinary team, and so we can bring people in as necessary to help with different phases of that process.
We've come online with very early stage clients who wanted us to brainstorm with them and figure out how to define the limits of the project. And we've also come along with clients who already knew what they wanted. Maybe they even already had a product out there, and we just helped them do some testing, some validation, and some debugging and iteration.
Before diving into like a specific pathway on a project, we always like to take a step back and look at the big picture and see what is the real underlying problems.
We call that concept design. Basically, we look at different ideas of how the thing might work without going into the details of like what's this dimension or what material does this have to be.
We'll brainstorm as a team and come up with different ideas, doing rough sketches on the whiteboard. And then I'll often take those sketches and do more detailed versions of them, sometimes bringing it into VR and lay out things in 3D space in a way that's still rough and sketchy. Really helps to lay out things where they should be and do design reviews with the team.
We like to bring in prototyping much earlier than most people and start really getting into the details of what the vehicle might look like. Doing fast prototypes, whether it's with 3D printing or Lego or some combination of both.
Prototyping is really critical for us to get into early, especially when we're designing something unconventional, which is pretty often here at Engineering Design Lab. We tend to take on the more unconventional projects.
We have a multitude of tools at our disposal. We can do a lot of things in-house with 3D printing, another rapid prototyping.
And one of the things we specialize in here is multidisciplinary optimization, being able to figure out, given the current state of the art and any innovations that we can come up with, what's the best solution, not just a good solution, but the best that it possibly can be.
We tend to focus on sustainable mobility, but we can also do things like custom scientific equipment, which we have done for government institutions such as Ontario Power Generation.
We were developing what was called the integrated current meter system, which is this massive apparatus for measuring the flow through hydroelectric dams. It was particularly challenging because Ontario has dozens of different hydro dams. Each one is unique, designed for its own river and setup. At the same time, it had to be incredibly reliable, so high stakes. And so we had to prototype several different joint strategies that would withstand the loads that we were placing on them and be reliable in the long term in this corrosive environment.
Working with World Vision Canada to do a design iteration on a device that helps health workers accurately inject a subcutaneous needle for contraceptive delivery. So we've been 3D printing multiple different versions of this device and testing them out on ourselves and like people in the team. It's probably not the best way of putting it. To see how well they work, which designs work best, and move forward with that for manufacturing.
Once we've got one or several concepts that we think and our client thinks is worth pursuing, we take those into detailed designs and then subjecting those designs to a whole range of engineering analysis.
This is where we, take it from a fluffy idea that has a lot of fuzzy edges and start hardening those down to a more solid concept.
Most recently, we've worked on the design of a high-performance battery pack for a motorcycle.
It's important in the design of electric vehicles to predict the temperatures that you'll see on a battery pack, because as you discharge the battery, it can heat up quite a bit. And in order to preserve the kind of longevity of the battery life, you want to keep them as cool as possible.
Something that was critical was figuring out what's the best way to cool these cells. Is it the orientation of the cells? Is it adding heat pipes? Where are we gonna direct the heat pipes to? How are we gonna make things fit securely and have good thermal contact?
So using various software tools, for example, computer-aided design and computational fluid dynamics packages, we can kind of model the products that we're currently developing and also run simulations on them to make sure that we're getting an accurate simulated model of the real-life scenario.
So recently we worked closely with a client to develop a walking robot. They had some specific requirements, things it needed to do, and we could only use one motor.
We developed some linkage mechanisms for walking with a single motor. And we also figured out ways to get that single motor to do other things, like wobble the head a little bit and like make the legs come out.
In the various iterations of the prototypes of this robot, we're able to reduce complexity, reduce part count, and increase manufacturability.
I would say the systems integration stage is where we actually turn the project into reality. And we start finding all the little minute problems that don't show up when you're just looking at it on a piece of paper.
A vendor put too thick of a paint coating on something, or, machine parts are out of spec. You can design the perfect part, and then when it gets made, all sorts of things happen, all sorts of non-idealities, and the integration stage is where you take those non-idealities and you have to rapidly basically solve those problems and make sure you can still meet the deadline.
And so part of our process and our specialty is addressing those bugs and those defects that come up, and very quickly and efficiently correcting whatever needs to be fixed to make sure that the solution works as expected.
Recently, we developed an electric amphibious vehicle. What was unique about this project was the open-ended nature of the brief. So we were able to completely come up with our own design, starting from scratch, from nothing. And we came up with a a totally unique vehicle architecture.
We had a lot of teething issues. Wouldn't have enough torque to get started. It would like dig itself into the sand, or it wouldn't be able to turn. And there was just a lot of sort of detailed dynamics that really showed up in the real world. So we figured out how to put some shocks on it in order to damp out some of the movements. We put different algorithms for the motor control in order to get it to be more consistent.
We did the entire systems integration of this complex vehicle all in-house. So assembling the different mechanical systems, getting our different motors and actuators installed, programming and reprogramming several times the vehicle firmware in order to address all the different kind of compatibility issues that came up as we were putting these systems together.
I was making sure that my code, if I sent the right command, that I'd spin the motor one way, speed it up, slow it down, spin the other way. Slowly doing these unit tests of each thing, the land motors, the linear actuators, the lights, the aquatic motors.
Within 5 months, conceptualize, design, fabricate, and test an all-new type of vehicle that will enable the Canadian Armed Forces to move equipment and personnel between Navy ships and unimproved shores. Most recently, we've been completing the prototyping of a vehicle control unit, which is a miniaturized computer that helps control and coordinate communication between a variety of different vehicle subsystems.
With e-bikes, there's a lot of ecosystems where you buy your handle, motor, battery, display, all from the same vendor, and it works together. The problem is that if you try to combine different vendors, you have an issue. I found myself often designing custom sort of intermediate stages to allow these two systems to be integrated with one another. And we've done this enough times that now we've identified a need in the market for hardware that we can drop in to develop projects quickly using a set of hardware that we've designed and we know is very capable.
It's easy to build one of something, but it's hard to build a million.
When you get to those scales and to those mass manufacturing processes, a lot of things can go wrong. And you might think you've got it solved, and then the next batch of parts arrives, and it's almost forensic. You need to go back and understand what's changed since then. Is there a new vendor involved? Is there a new material involved? Is there a new process? Is it machine settings? Is it the weather? What has changed, and what could be possibly affecting the quality of the parts?
Usually prototypes are very costly since they're one-off, essentially boutique constructions. So at this stage, we basically find much more scalable manufacturing procedures and maybe even slightly redesign parts to better suit such processes.
Any technique that can be used to manufacture anything, we have some expertise and experience in it. So when we approach a problem, we're not just developing a solution or a mechanism that will work on paper or in a computer or for a one-off benchtop prototype. We understand from the get-go what is manufacturable in an industrial sense. We can help our clients identify which manufacturing strategies are going to be the most cost-effective for a given product or a piece of a product. And we can also help our clients to fine-tune or understand complex problems within those processes.
There was an impact wrench company that came to us with a wrench extension tool. The purpose of this tool is to transfer the torque from an impact wrench from one axis to another axis about 10 inches away. They had seen this YouTube review of their product alongside a bunch of their competitors, and it wasn't coming up so hot. They had worse durability numbers and worse torque transfer numbers. We came and redesigned much of the wrench in order to improve these parameters. We redesigned the casing, some of the bushings, some of the sprockets in order to be more precise and to have lower friction. And we were able to make a tool that ultimately is a lot more durable and a lot more efficient.
The jet foiler is an electric hydrofoiling surfboard, or e-foil. We've been involved in that project for our client Kai Concepts out of Alameda, California for about 6 years. The jet foiler is a great example of our expertise in manufacturing at launch. At one point, there was a problem with the battery enclosures. They were too brittle.
The problem that we had with the injection molding was they were doing this in more or less an open air environment in southern China. And we started noticing that in the summers, the parts came out really brittle. Like you would drop it and it would just crack. But when you did it in the winter, it came out and it had the desired material properties, like it was pretty impact resistant.
We traveled to China to supervise the manufacturing, supervising the engineers, having them change various settings on the machine, changing the machines, changing the vendors altogether in some cases, in order to make sure we got the right quality parts.
Now we're able to have good products 4 seasons a year.
What really makes Engineering Design Lab unique is we're developing the toolbox and the skill sets necessary to make any small electric vehicle.
We've got such a wide range of very skilled, experienced engineers. I don't think I've seen this combination of people anywhere else.
Instead of going to 5 different consulting companies to solve specific problems, we can tackle all the different aspects of it right here. And that's what makes us like the Avengers of engineering.